What if I told you that everything you know about matter is wrong? Look around you. The table, the chair, the TV, all of this is solid. It can be touched, felt and measured, right? But in reality, all of this is just an illusion. And no, this isn't another pseudo-scientific fantasy. These are the latest discoveries in physics, chemistry and science as a whole. Just think for a moment about what matter actually is. Let's take ourselves as an example. We humans are walking machines that also appear to be matter. What are our bodies made of? At first glance, of organs, which make up about 1/3 of us, 2/3 water. But if we look deeper, we know that everything we are and everything around us is made up of atoms. Since ancient Greece, atoms were believed to be tiny, indivisible, solid balls, which were placed next to each other, formed the solid reality we experience. Over the years, however, a series of physicists, among them J.J. Thomson, Ernest Rutherford and James Chadwick, discovered that atoms are not indivisible at all. In fact, they themselves are built from even smaller elements, electrons, protons and neutrons. Thus the idea of atoms as the smallest possible particles was completely transformed. First, it became clear that each atom consists of at least two parts. At its center lies something small, once thought to be solid, called the nucleus. Around it orbits an even smaller particle with a negative charge called the electron. The electron is an incredibly fascinating particle. It moves extremely fast around the nucleus, and its exact position can never be determined. This is because it has a dual nature. At the same time, it is both a wave and a particle. Its behavior depends on what we measure and how the experiment is set up. In this experiment, if an electron passes through a double slit without us determining which slit it went through, it behaves like a wave and goes through both at once. But if we trace its path, it behaves like a particle, passing through only one slit as a solid phenomenon. In fact, electrons behave like particles only in the presence of an observer, a human performing the experiment. If no one observes them, they remain waves. We'll focus on how human observation influences them another time. But let's go to the bigger picture. Now we know that an atom has a tiny solid core at the center, and around it, in a vast empty space, orbit electrons whose nature is dual. Because we cannot know their exact positions, everything around the nucleus exists as a field of probabilities. Nothing is definite. Everything is a quantum potential, a cloud of possible electron locations. In fact, the nucleus accounts for about 99.9% of an atom's mass, yet it occupies only about 1/300th of its volume. To visualize this, if the nucleus were the size of a pea, the entire atom would be about as large as a football stadium. That stadium, however, is almost completely empty, or more precisely, it is a field of probability where the electron may exist. And speaking of the nucleus, we used to imagine it as a small solid ball, right? A pea, nothing else. But Rutherford and later Chadwick discovered that the nucleus itself isn't one solid particle either. It is made of protons and neutrons. Protons carry a positive charge that balances the electron's negative one. Neutrons, on the other hand, have no electric charge, but they stabilize the nucleus by reducing the repulsion between protons and keeping it from breaking apart. With the advancement of science, and especially quantum physics, numerous experiments have shown that similar to electrons, protons and neutrons also have a dual nature In other words, they behave as a wave when unobserved and as a matter when measured or influenced. It's also important to note that even these particles, protons and neutrons, are made of smaller elements called quarks and gluons. Here, we must make an important note. In the year 1900, the famous physicist Max Planck discovered that the energy of light is emitted in discrete packets proportional to the wave frequency, thus laying the foundation of quantum theory. This led to the understanding that a wave itself is energy. He explained this through his famous formula E equals hf. Without going into too much detail, E is energy, h is Planck's constant, and f is the frequency of the wave, that is, how many oscillations it makes per second. Now simply put, the more times a wave vibrates per second, the more energy it emits. Naturally, here we can also mention the most famous physics formula in the world, E equals mc squared, perhaps Einstein's most brilliant equation. Let's think about it for a moment. In it, E is energy, m is mass, and c is the speed of light squared. In words, Einstein showed that mass is not something separate from energy. It is energy, simply in a much denser form. So, after all this, we can conclude that waves and matter are two manifestations of the same thing, energy. One is diffuse and immaterial, the other is condensed and visible. Ultimately, what are our bodies made of? What are the table, the chair, and the TV made of? They are made of atoms, whose very nature is wave-like. And as we've seen, waves are energy. Therefore, we can confidently say that everything around us is energy. Energy vibrating at different frequencies, which is why it manifests different properties. And now let's think for a moment. What else is energy? Perhaps our thoughts? Could it be that energy influences energy? That our thoughts might shape matter, or more precisely, our reality? Well, that's a topic for another time. Thanks for watching.